Yeah, I'd like to thank the organizer for inviting me and give the opportunity to give a talk here. And with the invitation, Richard Weiss immediately told me what I have to speak about the contribution of Jacques Tits to the theory of finite groups. My contribution is to alter this title in finite simple groups. And I'd like to speak about something. If you try to do it, to speak about the contribution finite group, even finite simple groups, you need 3 talks at 15 minutes each. So I had to make a selection. I made some selection. It's a little bit personal, this selection. And maybe some of you would have done it differently. And on the other hand, I believe most of you know everything. I can't tell you anything new, but I hope I can give you a different view on some work of Tits related to finite groups. So let's see that I'm able to deal with this. Probably not, wrong direction.
We will. So try it. Next one.
Okay, good, thanks. Yeah, it starts, as usual, as everything starts, with everybody of us, with a doctorate thesis. It's May 1950, at least that's what Tits says in one of his papers. I do not have this. I have a paper from 1952, which has almost the same title. The only thing was notation was replaced by properties. That's the only difference in the title. And there are 4 papers from 49, a little bit earlier than this. And this tells you, because I'm born in 49, I'm not an eyewitness of Jacques Tits. All I can tell you is from the literature. The first time that I met Jacques Tits was 78 in Durham. Okay, the doctorate thesis is not really on finite groups. That's my problem now. You can simplify it a little bit. Look at this paper of Sassenhaus from 1935, where he classified the finite sharply threefold transitive groups. And he proves what Tits would say is a projective group. So contains a PSL 2p to the f of index 2. And from a view of a finite group theory, you can say the doctorate thesis is a generalization of this to the infinite case. It's not. His point of view is more the geometric point of view than the group theoretic point of view. But nevertheless, this is important. And there's something very strange in this paper. When you write a paper, you add at the end your references. So did Jacques Tits. But he also had references at footnote, which never appeared at the end again. Sassenhaus is a footnote reference, which means it's not so important for him. It's just a remark. It's not important in the proof. Okay. Yeah, so of course you knew that there's no direct generalization. There are counterexamples. That he knew. So he had to add something, and I'm not showing this because of the addition. I'm showing you because this word triplement, this is from the French statement. Triplement. What is triplement? Oh, triplement is n uplement for n equals 3. That's triplement. So n uplement, when I read this paper, I had to think, what's n uplement? Oh, it comes from n uple, an n tuple. So it's transitive on the n tuples, which means all entries are different. Okay. And then I looked at the theory and said, they are all wrong. Because this is not his definition. If you read carefully the introduction, then you see n uplement means is transitive on the n tuples, and the stabilizer of an n tuple is the identity. That's what we call sharply n-fold transitive. Okay, so why did he not use the word sharply n-fold transitive? There must be a French version of this. I looked at the master of everything, Camille Jordan, he says n fois transitive and gives the order of the group. That's the same. Zassenhaus said threefold transitive of smallest possible order. Who invented, in the hell, the word sharply n-fold transitive? I have no idea. Maybe Wieland? Something for historians. Who invented this? Nevertheless, you have to be careful reading this paper, even if you know this. Some theorems are wrong because he excluded the symmetric group. By technical reasons, he'd say, I exclude the symmetric group. And something he said, there's no group. Of course, the symmetric group is a group. You have to be careful reading this paper. Okay, here's the theorem in this paper which has to do with finite groups. You take now a fourfold, sharply fourfold transitive group, G. Might be infinite, on an maybe infinite set. And then he proves this group is not infinite because the set has at most 11 points. And 11 arises. M11 is an example. So 11 arises really. Oh, this result has been proven by Camille Jordan, what is this, 80 years before, for finite groups. He assumed the group is finite. That's the difference. This is a footnote reference also in his paper. Okay, I will give you a little bit from the proof, because the proof is amazing. So assume your group is sharply fourfold transitive. Then you pick 4 points, call them infinity 1, infinity 2, 1, and 0. Okay? Then you go on, you take the point stabilizer, so the stabilizer of this point, infinity 1. I call it G1, I guess. And the, G2, this is the point stabilizer of 2 points, infinity 2 and infinity T1. Then what he proved before in the paper, you have a group which acts regularly on the remaining points. Because the threefold stabilizer is sharply threefold transitive, and the paper is on sharply threefold transitive groups. Okay? Fine. And then he takes an element called I. Forget this word involution for a moment. It should switch one infinity to the other infinity and fixes 1 and 0. That's possible. The group is fourfold transitive. You can do this. What is if you square this element? Then it fixes infinity 1, infinity 2, 1, and 4. 4 elements. The group is sharply fourfold transitive. Whatever fixes 4 elements, the identity. So this is an involution. It's not an assumption, it follows. This is an involution. You take this involution. Good. That's something in Jordan's paper is different. He gets the involution by Cauchy's theorem. The group is finite at even order. There are involutions. Okay. Now, before, when he treated the sharply threefold transitive groups, he has proved that on this set you have a multiplicative and additive structure. And he also makes a footnote to Zassenhaus. That's what Zassenhaus calls a near field. And this I, because it's normalized G2, it normalizes gamma, and it respects the multiplication in gamma, so it respects the addition on this set. Okay, that's important. Now you take any element in this set and take the image under this involution, IA plus A, call it C. Because I is an involution, C is a fixed point. I has at most 3 fixed points. It's not the identity, it switches 2 elements. So there are at most 3 C's. How many A's can lead to the same C? That's the question. Could be infinitely many, why not? And here comes the trick. No, here comes not the trick. That's what I said. How many A's? Now comes the trick. Oh, but that's one too much. Here. Good. You have this element TC. You can prove this exists. which moves x to c minus x. And then take the product IT and apply it to A. With little calculation, you see it comes out A. This element ITC has this A. C is fixed. Any A which leads this C is now a fixed point of ITC. ITC is not the identity because I is not in G2 and TC is in G2. So the product is not the identity. So this element has at most 3 fixed points. So any C has at most 3 A's. 3 times 3 is 9. And we dropped 2 elements. So omega is at most 11. It's a very easy proof. Yeah, then he constructs, really in this paper, M11, indicates 11, that is the only example. Then he showed that if you go to 5, sharply 5 of transitive groups, okay, then the stabilizer is, of course, sharply 4 for transitive. So omega minus 1 is at most 11, so omega is at most 12, and you get M12, and then he proves the, oops, that goes in the direct, oops. Here, yeah. And then he shows there are no sharply 6 for transitive groups for at least 6. You have to read this, yeah, if you drop the 13, then you have to read it in this way. If you have sharply n for transitive group, n at least 4, then you're looking at a symmetric group. So his statement is there are no sharply n for transitive groups. Okay, that's all well known to Camille Jordan, no question. And he writes in this paper that this is not the important fact that he proves the same as Camille Jordan in the finite. The important fact is there are no infinite sharply 4-fold transitive groups. That's the point. Okay. So the second point I want to speak about is, I hope, yeah. Okay, I'm in time. Is the relation of Tits with sporadic simple groups. He loved a lot of sporadic simple groups. One group he really loved was the whole Janko group. And the other one I would say was the monster. He wrote several papers on the whole Janko group. This was constructed by Hortz and Wales and proved uniqueness in a Journal of Algebra paper in the following way. They proved whenever a group J2 exists, it has a subgroup isomorphic to U33. And then they tried to construct J2 out of U33. They start with U33. U33 acts on a vector space, and you have a geometry. So you are able to do the following. From the vector space here, you take the isotropic lines. That's the wrong way, I have to put it here. There are 36 of them. No, that's the point. It's right, so it has to be here. And then there are subgroups L32, and there are 36 of them. And then you join this with all these 36, and in a certain way you join these. They did not join it. They just put this set on it, and on this, of course, U33 acts, because it acts on the conjugate of this group, acts on this. And then they produce an additional involution on 100 points, which also acts on 100 points. And in the Journal of Algebra, you see these beautiful 3 elements on 100 points. And then they say, by computer calculation, we has the same order as J2, and then they get this is J2. So that's the construction of Hall and Wales. Tits gave a conference report about a different construction of the Hall group, and he thanks Marshall Hall. At this time, the paper was not appeared, so he thanks just Marshall Hall because he gave a talk in Oxford, and obviously Tits referred to this talk, and he thanks Hickman-Sims, because the Hickman-Sims construction was then with the graph which I just dropped. Okay, what was the great idea of Tits? U33 is the same, isomorphic at least, as G22 prime. Okay. G22 is by a factor 2 larger than G22 prime, so he constructs not J2, he constructs the automorphism group of J2 using G22. Okay. So what did he do? No, this is one too much. Oops. There should be something in between. Ah, here. Good. Yeah. So G22 acts on a generalized hexagon. That's how it's defined in a certain way. Lines of the hexagon. And then he identifies the 63 points of the hexagon with the points of a hyperquadratic. He has a whole paper of the triality. The point is that G22 is the fixed point group in D4 under the triality automorphism. There you get this relation. Now, in this hyperquadratic, you have subplanes, not just lines and points, you have planes. And he defines normal planes. So if you have a plane, there are lines in it, and the plane is called normal if none of these lines are lines from H. So you get normal planes, and then he defines a relation called associate, that two planes, normal planes, are associate. I'm not going into details. And there are 36 pairs, exactly. So he also gets the sets in a different way. And then he introduces a graph structure on it. So this point is joined with everything, and here with some relations, these points are joined. And then, so the G22 acts on this, no problem. And then he defines an involution in a very geometric way. And he writes, well, it was a talk, he says, that this together with G22 will get the automorphism group for Hall-Janko, provided you can prove that this element which he writes down really respects the relations here on the graph. It's a graph automorphism. And then he says, this is easy to calculate without a computer, but he never gave a calculation of this. Okay, we believe that he did it somewhere. I'm not sure that somebody else ever did this. But what was the basic idea? U33 is G22 prime. And in a lecture on sporadic groups, 1970, where he spoke about the sporadic groups known at this time, he ends this with a philosophy. He calls it philosophy, that the existence of sporadic groups is really somehow dependent on existence of exceptional isomorphism. We have seen one. Some exceptional embeddings of groups in each other, or some exceptional Schur multipliers. That was his philosophy. Let's see. Yeah, he dealt with further sporadic groups. I just list one. He gave, not just the simplified proof of the monster group. He really worked on the monster group. He looked at J2 again. He gave a beautiful proof that the three Conway groups are all simple. But I think I don't have time to speak about this, so I will go switch this. Yeah. I call this the honorary sporadic group, the 27th sporadic group. In a paper from 1964, he dealt with the regroups, twisted F4. And the twisted F4 come from F4 in the same way as the Suzuki group comes for the the Suzuki groups come from the four-dimensional symplectic groups, certain way. These groups have a Bn pair, and of rank 2, and they are all simple besides the smallest one. This he remarks in this paper, and here's the proof. So you can, twisted F42 is a Chevrolet group. You can generate it with the 12 positive root elements and the 12 negative ones. There are 24 elements and the relations in between. They define this group. Now the point is that some of these root groups are elements of order 4. So squares are also roots. So you can drop these squares. You don't need it. There are remaining 16 elements. And he produces, with the 16 elements now, relations. And he looks at a group defined by the 16 elements and the relations. And then he proves this group has a Bn pair. He can calculate the order at the same order as twisted F4, so they define twisted F4. So that's not important, but important is now this remark. If you replace in your relations ui by -1 to the I, the relations are still satisfied, which means the group with 2 elements is an example, which means that the defining group has a subgroup of index 2. So it's not simple, has a subgroup of index 2, and then he proves the subgroup of index 2 is simple. This is what we nowadays call the Tits simple group. It has no Bn pair, but it's not sporadic because it's member of a series. But you should honor this. Okay, I think I come now to what you all think one has to say when one speaks about contributions of Tits to the finite simple groups. That is the just mentioned 74 paper on the buildings of spherical types and Bn pairs. He worked, as I can see, since 1953 on this problem. That is the final step. And in a paper in, where is it, 87, he writes that the initial motivation for the theory of buildings was to produce an algebraic analog of the, in a geometric way, of the exceptional Lie groups. In 1953, before Chevrolet came along. That's the Chevrolet paper in 1955, where he constructed all these Chevrolet groups we know today. Let me tell you the difference between Chevrolet and Tits. So take the group A5. You learn in linear algebra it's a group of even permutation on 5 letters. You can consider it as L24. And it's the group of, you have to add here a group of the determinant 1. Otherwise it would be wrong. This is more or less the Chevrolet point of view, the representation of the group. Or it's a group of rotations of the dodecahedron. That's the Tits point of view. You have a geometry. When you look at the group which leaves this geometry invariant. So he writes somewhere group theory is more or less the theory of symmetry. And that's exactly his point. He starts with the geometry, and the groups are automorphism groups of this geometry. So the Hen-Eck problem is solved for him. Okay. In this bill, one of the things, if you have this philosophy, then one of the things he must have hated, in the paper he couldn't construct all buildings by themselves. For example, for E8 he needed the existence of the Chevrolet group E8. That was one of the reasons to write this paper with Mark Ronan, where they construct really building without groups. And he writes, now we have an E8 building without the group E8. This was very important for him, I'm sure. Yeah, and there's a Bn pair in the title. Now, groups with the irreducible Bn pair lead to a group with an irreducible spherical building. That's the connection. Good. So far, the work of Tits. Now, what's the relation with... I still have 20 minutes? Yeah. With the finite simple groups now. Now, Richard Brouwer told us to classify finite simple groups by their centralizers of involutions. It's a very simple statement. So let's do it. Take your favorite finite simple group, take an involution, take the centralizer, say, oh, let's see whether, this is the only one. Now, Brouwer told us there are at most finitely many. It could be very many, it could be thousands. It's also finite. The classification tells you finite is 3, at most 3. Okay, now we take my favorite group. I will not convince you that it's your favorite group. E6 of Q, and take Q equals 2. It acts on the building with this diagram. Okay? We take the centralizer of an involution. The centralizer of an involution in this group is an extra special group of order 2 to the 21 extended by the group L62. And take the centralizer means really the multiplication table is known. You can multiply any 2 elements. No problem. And now you take an abstract finite simple group and assume that you have an involution that the centralizer is isomorphic. Show your group is E62 in this case. So what you do, I forgot to say, this is the parabolic subgroup G4 in the Lie groups speaking. Now you do something, you work a little bit, and you produce the normalizer of the group generated by 2 conjugates of this set, and in this case you get the group, I think G3. That's the group you get. And you work a little bit more, you take the normalizer of 3 of this conjugate, and you get this group. Okay, you see this L3 and 2 L2s. Everywhere the multiplication table. All details are known. So you can prove this group has a Bn pair, no problem. You have everything. Good. And then you quote the classification of Jacques Tits, and it tells you, you're looking at E6 No problem. In the introduction of his lecture notes, he writes, my idea of classification of finite simple groups is you produce a Bn pair in this group and then use my paper. The next sentence is, John Thomson told me, if you have a Bn pair in the group, you know so much about this group, you don't need this paper anymore. Something is true with this. Okay, so far so good. We cannot classify all finite with multiplication tables and things like this. At some place you have to prove some structure theorems on centralizers of involution in finite simple groups. And the outcoming will not be multiplication tables, there will be structure of things. And let's go to E6 again. And now the structure theorem tells you you get a centralizer of involution which is similar to this. What does it mean similar now? It means that I know that this Q to the 1 plus 20 is still a special group. L6Q is still what it is, L6Q. And I will know that L6Q acts on this group with the exterior cube module. But I will not know whether there's a complement L6Q or how it really acts on the extra spacing group, that's module, the G factor I know. And I can do the same as before. I get this group and I get this group, but now, both are on there. But now, I do not have that this is G4, G3, G2, 5. I just have rough structures of these groups. I cannot produce a BN pair. I cannot use Tits. So what to do? Who helps? Nobody else, you will guess, as Tits. Oops. I'm always, yeah. The local approach is this most important paper in this relation. Because there he related buildings to chamber systems. A chamber system of type M. You have a diagram, he defines what it means, a chamber system of type M, and the nice point is any building with a Dinkin diagram of type M has a chamber system of type M. So what? We have building, why should we look at chamber system? Now the nice thing with chamber system is, Cayley told us, when a group acts on a set, you can forget this set. You see everything inside of your group. Any set on which a group acts is hidden in your group itself. So the chamber system exists in your group. And how? Now, let's do it in this way. We take a Borel subgroup, B, and the chambers are then just the cosets of B. And we take a minimal parabolic, and two cosets are I adjacent, two chambers are I adjacent, if the cosets of this minimal parabolic are the same. So you see it totally inside of your group. And this you can mimic in your group H. You define B as the normalizer of a pseudo 2 subgroup. That's what it is in a group of Lie type. Good. Then you take groups in which B is maximal. Later on, one had this generalized a little bit. And a group should be generated by this, PJs. This we call a parabolic system. And one can see, in the same way as in the Lie type group, that a parabolic system leads to a chamber system. Okay. So what now? Why is this a chamber system of a building? Or why is this a building or something? And here something came up. So 77, 78, maybe a year earlier, the notation of a diagram geometry and the Buchenhaut geometry, these things came up. In 78, and at the Durham conference, Tits gave a talk on Buchenhaut geometries, where he promoted to look at Buchenhaut geometries and classify groups with Buchenhaut geometries, and maybe to introduce some axiomatic way to look at Buchenhaut geometries. Nevertheless, people start really afterwards to work on this geometries, and for our purpose now, important is a paper. Oh, this is, by the way, the geometry for the monster. Is a paper of Timmersfeld, where he looked at parabolic systems and classified them as long as they belong to diagrams where you just have single bonds. And for us, it means just that we are looking at A6. E6 of Q. So our group is a subgroup of E6 of Q. And has the same pseudo 2 subgroup. And now another theorem comes, the Borel-Tits theorem, which tells you, if this is the situation, if you have a group of Lie type and you have a subgroup which contains the pseudo subgroup, then this is a parabolic. And if the OP of this is trivial, it's a trivial parabolic, that's the whole group. That's the way it goes. Okay. Yeah. So that's not all. there's a revision of the classification of the finite simple groups. And here's a paper I like to speak about a little bit, not very detailed. So our setup is here is a little bit more general, but you may think H is a simple group. And the P part, and you want to try to prove H is isomorphic to G, where G is a Lie-type group. And they should at least have the same P part. Okay. Now, what we did up to now, we started with the group H, we produced the parabolic system, we looked around, has somebody classified parabolic systems of this type? Yeah, yes, and then you go from this classification over to the spherical buildings, the classification of spherical buildings, and you get your result. And Meyer-Frankenfeld said, this is ridiculous. We have one group H and we have one group G, and we want to prove they are isomorphic. Why should we go this detour and come from the other side and say, oh, they are isomorphic? Just produce an isomorphism. That's all you have to do. Okay. Let's look at this group E6 again. So you take a collection of subsets of your diagram such that any rank 2 diagram is contained in one member of this subset. So you can, for example, you can take as D 5, 6, 3, 5, 2, 3, 1, 2, 3, 4. That's fine. But this gives you much work later on. So you should take as many as, yeah. This is beautiful because we have this. This comes from G4. And this is beautiful. So we have this satisfied. And now we do the following. We have here the group H, and here the group G. And for any D, here are just two Ds. Call this D1 and call this D2. We have a group HD in H. And they should generate H. Otherwise, I just get a result about a group generated by these two. Okay. And then, on this side, this group acts on a building of this type. So you have a residue of type G, D1, I call it with a bar, G, D2 bar. What is induced on this residue? For example, G, D1 bar is an L6Q, nothing more. And then you have an epimorphism from here to here. This one and this one. As a large kernel, of course. You have a restriction of the kernel, and they shouldn't be so arbitrary. On the intersection, they should be equal. They should fit together. And what you then can do, you can move this chamber system from here to this group. And you get a chamber system here of type M. And you can put all this together, in this case there are just two isomorphisms, to an isomorphism. So how you get this chamber system? So you have here a Borel subgroup BD1 bar, BD2 bar, which gives you here Borel subgroup BD1, BD2. You could the group generated, call this the Borel subgroup, and in the same way you do this with the minimal parabolics from here containing this PIs. This gives you here the minimal parabolics. And the only thing what you do not see, you see all this which are in a rank 2 residue. But you don't think this because you have no assumption made about this. 1, 4. So if they are not connected on this side, the minimal parabolic should just commute. That's what they do in the Lie-type group. Yeah, and if you have this, then the result is, then H is isomorphic to G. You can produce this isomorphism. That's the way we do it now in the revision, the identification of Lie-type groups. So, why is the work of Tits so important for identification or classification of groups of Lie type? These are the generic finite simple groups. On one side, you have the world of simple groups. On the other side, you have the world of buildings. There's a river in between. John Thomson told us, when we deal with simple groups, we should deal with p-local subgroups, normalizers of non-trivial p subgroups. So we have on this side the p-local subgroups. Tits gave us the chamber systems. Chamber systems are defined by these PIs. The PIs are all p-local subgroups. They're the normalizers, the OP of PI. So Tits gives us p-local subgroups which define the building. So on one side we have this p-local subgroup in simple groups, which gives parabolic systems. The chamber system in a building, if I produce them inside of the group, is just a parabolic system. So the bridge is the parabolic systems. So we can join the buildings with the groups and vice versa. That's what is a beautiful thing, a match in heaven between buildings and simple groups. Thank you.